Hello everyone. I'd like to welcome you all to this sixth course under the headline of Suitable Conditions for PV Installation, making part of the training program supported by SESA project. In this video, you will learn first, solar resource map, second, meteo station and their rules in solar PV pre-sizing, then ROEs for different categories of PV modules, for example, polycrystalline, monocrystalline, and thin film especially. Then we'll pass to KPIs that determines the suitability of PV systems, performance, investment, operation, and maintenance. Finally, tools developed by Green Energy Park. In the coming slides, we will be talking about solar resource map, divided in three main parts. Let's begin with photovoltaic power potential, represented by kilowatt hour per kilowatt peak, varying across the whole map from 2.0 to 6.4 for the daily total, and for the yearly total going from 730 to 2337. We will go now to, we're still talking about solar resource map, and now it's global horizontal irradiation, GHI. In this map, we will represent the potential of the irradiation. Its unit is kilowatt hour per meter square, going for a daily total from the list value, which is 2.2 approximately, up to 7.4. And for the yearly total, it's 803 up to 2702. We see that the concentration of the horizontal irradiation is well present in Africa, which is our aim for the SESA project. For the last part of the solar resource map, we will be talking about DNI, which is direct normal irradiation, going for a scale from 1 to 10 kilowatt hour per meter square, and a yearly total of 365 up to 3652. We see it's the same case as the GHI, or the power potential. It represents the direct normal irradiation across the whole continents, also the countries in this map. Now, what is a weather station and what is its role? A weather station is a structure that contains a set of instruments and equipments to measure environmental conditions in order to provide information for the study of climate. These stations are also used in the field of solar energy, as weather conditions have a considerable influence on the performance of solar systems. However, solar weather stations have additional and more specific collectors. In this slide, we will see the types of categories and implementation of the solar sensors and their roles in our study. We can talk about performance evaluation and fault detection at operational solar power plants first. Two, we talk about pre-feasibility studies of a large-scale solar projects, and we need this kind of sensors to give us the right KPIs, the variables that will be driving the main studies. And then finally, the validation of satellite meteorological databases and the development of solar maps. Now, in our solar weather stations, we have 7 installed and 3 outgoing. We have one in Ben Gurir, another one in Mysore, third one in Erfurt, fourth one in Zagora, fifth one in Fqih Ben Saleh, and another one in Yusufia, exactly in Zinda. Then Khurib Sidi Shinan, Gilmim Zag, which is outstanding, Gilmim Laborat, the same, and also Safi. slide, we will be talking about the soiling sensor. Well, a PV soil sensor measures performance losses caused by the accumulation of dust and other deposits on the glass or the surface of the PV model. So we have this kind of moisture that goes in the surface of any of these solar panels, and then we, as the study goes, and we need this right model to describe what's happening with our solar system, we need to quantify the direct effect of, for example, the soiling or the how we say, the accumulation of these deposits on the glass. Here is an example of measured solar irradiation under different circumstances. For example, for a cloudy day, and then for a shiny good day. So we see that there is some disturbances in the process of generation of power, or the PV output power, in the two main and two upper diagrams. And then we have the normal shape of the PV output power, which is simulated and measured, and it is the normal output. And those are real examples taken from the GEP station. Now going to the characterization of the solar source, we see that we have different categories, we can say categories of the solar source. We go from real-time measurements, which are mainly electrical, then go into the SAM skies imager, for example, then satellite image, and then NWPs, in which we can represent those data in a time series of seconds, for example, for measurements, and minutes for sky imager, then hours for satellites, and so on. In this slide, we will be giving you just quick hints. I'm gonna let you focus on the values, but I'm gonna just tell what are the parameters that we use in this evaluation. For example, in Germany and worldwide, we're talking about PV installation market, cumulative installation, PV power generation, the electricity share of PV, some categories and technologies of solar PV production and record solar cells, etc., etc. So those are some quick hints of some values that we can use later on. For the PV production by technology percentage of global annual production, we have the materials usage for silicon cells has been reduced significantly during the last 16 years, from around 16 gram per watt peak to less than 2.5 gram for the same amount of power, due to the increased efficiency, thinner wafers, and diamond wires, saving as well as larger ingots. The energy payback time of PV systems is dependent on the geographical location. PV system produced in Europe and installed in Northern Europe needed around 1.1 years to balance the input energy, while PV systems in the south equal their energy input after 0.9 years, depending on the technology installed and the grid efficiency. Finally, a PV system located in Silicon with wafer-based silicon models has an energy payback time of around 1 year. Assuming 20 years lifespan, this kind of system can produce 20 times the energy needed to produce it. For the annual PV production by technology worldwide in gigawatt peak, we have approximately 190 gigawatt peak PV models production in 2021, and the shares are usually taken from monocrystalline silicon to polycrystalline, and there's a quite small share for thin films. Those are the statistics of 2021 production numbers reported by different analysts and vary to some extent. Okay. For the current efficiencies and power of commercial PV models sorted by technology, we have a total weighted average efficiency of crystalline silicon wafer-based models is 20.4% in the fourth quarter of 2021. Weighting factor is total shipment in year 2020. Lowest model efficiency in this group is 16.3% and the highest value is 22.4. The top 10 manufacturers represent about 78% of total shipment volume and origin mainly in Asia. Predominant the crystalline silicon technology is monoper with half-cut cells and multi-bus bar. For the historic trend in energy payback time, we see some harmonized studies data for monocrystalline silicon rooftop PV systems. We see each time the cumulative production doubled, the FPBT went down by 12.8% for the last 24 years. And we see the cumulative production and the PBT in years for monocrystalline PV rooftop systems. Okay. Now let's go to energy payback time of silicon PV rooftop systems, geographical comparison. We have the rooftop PV systems that are using monocrystalline silicon cells produced in China. EPBT is dependent on irradiation, but also on other factors like grid efficiency, for example. Better grid efficiency in Europe may decrease the EPBT by typically 9.5% compared to PV models produced in China. I hope you understood EPBT, but it's an abbreviation of energy payback time. The global weighted average LCOE was in year 2021 for large PV systems around 0.041 euros per kilowatt hour, which means 41 euros per megawatt hour. And the LCOE decreased by about 17% on year-to-year basis in the last 11 years. For the global weighted average total cost for large PV systems was 725 euros per kilowatt peak installed in year 2021. Total installed cost for large PV systems decreased by about 14% on year-to-year basis in the last 11 years too. For tools developed by Green Energy Park in Morocco, we have in the current context of the market interest in the use of renewable energy resources, the Moroccan and African territory constitute a very important deposit still underexploited by lack of information. Indeed, exploitable areas offer remarkable potential for the development of renewable energy. Green Energy Park developed cartography which was made available for the Kingdom of Morocco and for Africa in web application format. It makes it possible to systematically assess the solar, wind, and the cadastral potential of all territories. Cartography is based on meteorological and satellite data. Thus, any user will have a better vision in terms of support for the identification of areas with high potential for each place in Morocco and Africa for the benefit of decision makers, investors, and researchers. The main objective of cartography is to provide quick and easy access to data on renewable resources and photovoltaic and wind energy potential on a Moroccan and African scale at the click of a mouse. Cartography is a decision-making tool for public administrations, companies, and individuals, redefining the value of a plot of a land in relation to the solar potential it can provide. It is also a communication tool for local authorities with attractive and educational rendering. Thank you for your interest and willing to collaborate with our expertise.